You are welcome once again. We'll be looking at potential errors in measurement. I'm sure we are familiar with this potential error. The reason I want us to discuss potential error is because most of the time the error are due to the way we handle our study, and we can do a lot to reduce this error through our study design and through data analysis. So that's where statistics comes in. And most of the, statistics is very important, even from the conceptualization stage of your study, even your sampling method and many other things, the way you select, the statistical method are used. It's not all the time you use equation or whatever. There are some things you do that are actually part of statistics. Now, what are errors? The errors simply mean the difference, between a measured quantity and its true value. When we say measured quantity, this one cut across. The same way is applicable in physical science like physics and chemistry. It's also applicable in biological science, in medicine, in biology generally, and even in social science. Quantity, the difference between a measured quantity and its true value. It is only the physical quantity, you can say, as the name implies, physical. Sometimes what you measure in biology you may not even physically see it, you may not see it physically. Sometimes it's something you can perceive physically also. But sometimes, like a psychiatry, they measure, they want to know if somebody is depressed. They use some scale, some questionnaire, and by the time they ask series of questions, they tell if the person is depressed or not. They are measuring something, even though they are more like conceptual scale, whichever way, either physical, something physical scale, or something conceptual. You are trying to measure something. Now, for us to extend it to study generally, when you try to find out something in the population, what you are interested in finding out exists in population as a parameter, the summary of something, of a characteristic. For example, you may want to know prevalence of hypertension. Yes, it does exist in the certain population, and sometimes it's only God that knows the prevalence, but it's there. It's a parameter. As a researcher, you carry out a study, but you only have access to sample because of logistic and funding issue. You cannot attend to the whole population. You now take a sample which is subset of population. Whatever you estimate there is called statistic, whereas what is in the population is called parameter. So statistic is an estimate of parameter. So you may say, oh, the value, the prevalence of hypertension in that community is 25%. If it in the real sense is 30%, there's an error. If it is 23%, there's an error because your estimate is not exactly what is in the population. It's an error. So whether you know it or not, it's an error. So it doesn't have to, is the way it is true to physical measurement, same thing with study generally. The parameter you are interested in the population, it does exist, it has a value, you may not know. But when you now carry out your study and through your sample, what you get in your sample is an estimate of population parameter. And there may be error. So you see, sometimes the error may come from different stages of your study. Even if you are trying to measure somebody's weight, it's part of it. You are collecting blood sugar. If you didn't collect it at the right time, it will contribute to the error. If you are measuring somebody's weight, if you are not using the weight scale, is No, for some of those people you are attending to, the weight scale have fault and you can't get it accurately. At the end of the day, when you summarize, this is the mean weight for the people. It may not be the same with what is in population. There's an error. So when we talk about error, the way it is applicable even to physical measurement and individual measurement is the same way it is applicable to the whole study, the estimate, the statistic or the parameter you are trying to estimate through your statistic. So having laid down that foundation, you can see the difference between a measured quantity and its true value is the error. It's very simple mathematically. From that, you know that this is error is equal to T true value plus, though, can you see, this is what you find. This is your mark. It's called the true value plus the error. So if you say that, like the example I gave, if the prevalence of hypertension is 25%, and your research you get 30. So the 30 is what you get, but the true value is 25, the error is 5. If you get 35, the true value is 25 or 30, or maybe, okay, the true value is 25, you get 30, the error is 5. If you get 20, the error is minus 5. It's still there. The difference is 5 for both sides, either less than or greater than. Now, this error, the deviation from the true value is the error. There are two types of the error. We have the random error and the systematic error. The systematic error is what people refer to. So you have two types of error measurement, random error. So sometimes even both of them can occur at the same time. That is why the last equations, okay, this is the value you got, this true value plus the random error of the systematic error. So the random error and systematic, if they exist at the same time, they will contribute to the error. So you're going to find out when you say that the random error, you're going to look at them, it can be removed completely. In systematic error that can be removed completely, while the random error cannot be removed. We discussed that. Now, the random errors versus systematic error. Please, if anybody have question, you can just chat it so that when we finish, we can attend to the question. You can chat your question now so that when we just finish, we can attend to the question quickly. Random error occurs when the value of the sample measurement diverges from that of the population value due to chance alone. So what causes random error is due to chance. It's not the way you carry out the study, chance of occurring. But you can still improve. If something occurs by chance, you can still find one way of reducing, circumventing it, but you may not be able to remove it completely. Because if you are sure that something is due to chance, you try to be more stringent what you do, make sure to reduce it, but you cannot, since it's due to chance. So you cannot be 100% sure that you cannot make that error will not occur. That is random error. Random error causes inaccurate measurement of association cause. That is, you say association between, just like any estimate or association between two variables, you may error. Random error can make sure that cause inaccurate measurement, either it reduces it or increases it. Systematic error or bias is the same thing. Either you call it systematic error or bias. Of course, when results differ in the systematic manner from the true value. Can you see the first one, the random error is due to chance, while systematic error is due to systematic in a systematic manner. So I will explain it was systematic here. From the next sentence, it is overestimation or underestimation of parameter of interest due to way and manner the study was carried out. That is what makes it systematic. It's the way you carry it out. That is, if you improve on it, you may remove it completely. But that is what they say. That's what literature say. But me, I want to differ slightly. That yes, you can reduce drastically systematic error more than you can reduce random error. I doubt if you can actually, in many situations, can actually remove it completely, even the systematic error. So if that's the case, why should somebody, okay, people carry out study, they feel they have, yes, they have removed systematic error. But the same person in the next study, you improve on his method. If you need to improve, if you are not perfect, you need to improve in your method. That show that what you did last year, you thought it was, yeah, it was okay. Then you discover that, oh, I will have done this. That show that there's no way that show that you didn't actually remove all the systematic error. So that's my own opinion about that. But theoretically, it is believed that if you can remove it, that you can do much more to remove it than removing random error. It is an error. It is error caused by factor other than the causes of random error. So if anything that is not random error is systematic error, because the random error, you cannot do much about it. They are there. You can just try to improve it, but you can do much. You can do much about systematic error, but because of that much, what is much? If two people are to carry out similar study, to the extent to which they are able to remove systematic error may differ. If that's the case, so if it differ, you say both of them completely remove systematic error. Even the study you think is the best may not completely remove it. Then you can improve in such a way that you can be sure that after you have done many things, the estimate close to the real parameter, closer than it will have been if you have not carried it out well. So in a summary, random error, random error, systematic error. The random errors can be, the sources of this random error are three: individual biological variation, sampling error, measurement error. So the cause of, so in a physical science, if they are to list the cause of random error, it may vary slightly from our own, but measurement error is constant, is there, both in physical and biological science. Though even biological science is physical, but those other ones, yeah, both in physics, chemistry, and other sciences, compared with biological science, even social science, measurement error. But of course, individual biological variation does not come under that, their own. Sampling error is applicable everywhere. So we explain how those factors cause random error. Then, why systematic error? We have systematic error bias. People can tell you over 30, even 40 bias. But if you look at it, actually, they are not actually tied. They are the causes of bias. So these are the things that cause systematic error. Then you can actually classify them under this category: selection bias, information bias, and confounding. So under each of them, especially selection bias and information bias, you can see a lot of, especially selection bias. There are categories, even more than 20. Anything that can cause selection bias, people just bring it out as many things can cause it. Many things, uncountable. So people can bring as okay, they just give it name. Bergsonian bias, this one bias, hospital bed bias, many things. So it's whatever. Even funding bias, if you decide to fund a particular, so it will affect the study and you generalize. Somebody, and you are going to generalize the study, but the funder is looking at some segment. So when you are generalizing, you may generalize beyond that segment. So that's funding bias. So we look at it. Then random error. That's just a short classification. Let's quickly look at random error. Three major sources we have just highlighted or itemized in the diagram there: individual biological variation, sampling error, measurement error. Random error may never be completely eliminated since we often study only sample of the population. Let me explain this theory before we move down. Individual biology variation, like blood sugar. If you want to, you yourself, you know that if you want to, okay, fasting blood sugar, okay, person should not eat after 10 o'clock. There's some people how eat, even if the type of food people eat differ, and you are studying population, many people involved in your studies come, they don't eat after 10 o'clock, come very early by 8 o'clock. So some people eat the last meal by 7, by 5, some by 10. They say it should not go beyond 10. So when they come by in the morning, you start taking from 8 as they are coming, maybe by 11 or 10 you stop. But the issue is that even the same person, if you take the blood sugar by 8 o'clock, if you take the blood sugar after 5 minutes, you won't get the same result. You are taking it after 5 minutes or after 10 minutes. Somebody that, okay, the last person, okay, I will not take it beyond 10 o'clock or 11 o'clock, so that it will not be, because they say that if hunger come, glycogenesis now coming. So the issue there is that the person you took the blood pressure from, blood sugar from by 10 o'clock, if you are taking it by 8 o'clock, you will get the same result. So even you, they just take your blood sugar pressure now. Within 2 minutes, take the blood pressure, you will not get the same thing. Even within the body, there are constant changes. So there are individual biology variation. And the way different people handle different things also differ. So you see, when you are selecting maybe 400 people, 300 people you are studying, even there are variation between different people, how their body handle a particular thing, how their body handle sugar, even the body respond to change in blood pressure and many things. Even within individual, there are changes. So you cannot be sure that you are getting the accurate result. But there's nothing you can do apart from being stringent. Like what? That's why when people take something like blood sugar now, they make sure that they don't take it beyond certain time. So those are the measures. But it has not completely eliminated the error, but it has reduced it. If they don't do that, in fact, the error will be much. So you can understand individual biology variation. Then sampling error. The meaning of sampling error is that in as much as the researcher did not take the whole population, you didn't study the whole population, there's no way what you get with your sample, it can never be equal to the parameter. In as much that you don't take, because if you are studying the whole population, you take your measurement from whatever you get, okay, you can say, okay, you have removed sampling error. So you can only completely remove, it's the only one you can completely remove there among the sources of random error. If you study the whole population, even with that, does not mean that you have removed all the random error, because the measurement error is still there, the individual biologic variation is still there. But by increasing the sample size, you reduce it also. So it's part of what you do in reducing sampling error. Measurement error. This one now has to do with the way you take your measurement. In measuring using certain scale, you cannot be 100% accurate. That's why sometimes you like if you are measuring blood sugar, blood pressure with the barometer, this speed, the one we usually accusing, the one we usually use in the hospital. If you look at it, it's not digital, it's analog. Because when you even though it's calibrated there, but people round up something, you only hear 120, 125, 130. They know 121, no 122.3. But with digital, it can give you 121, 122. So it can give you that. So sometimes the measurement, the scale you use, it affects your measurement. So somebody can stand on weighing scale and somebody You know, you say I weigh 71. Another person say I weigh 70. Someone say, okay, I weigh 70.1 or 70.5 rather. So you see, the measurement error is there due to the way we take measurement, the level of accuracy and calibration. It affects our, at the end of the day, it affects the output. Of course, you can reduce it also by following protocol, by being stringent. You know, if you draw protocol, so especially protocol being stringent, that's the way to reduce individual biological error due to individual biological variation and measurement error. Of course, for sampling error is to increase the sample size, you reduce it. So if you put all those on there, you'll be able to reduce your random error. Sampling error is usually caused by the fact that a small sample is not representative of population. Yes, I've said that. In as much as I didn't study the whole population, then there is sampling error. So there will be no sampling error if you study the whole population. So in individual variation always occur. No measurement is perfectly accurate. Yeah, I've said that. Now, how to reduce it? I think I've said the best way to reduce sampling error is to increase the sample size, because that's the best way. Increase the sample size. Measure unless if you can study the whole population, sampling error is hard for that study. There is no other situation that, in fact, in most situations, you cannot do that. Measurement error, reduce this stringent protocol, making individual measurement as precise as possible. By training, when you train, and you also do reliability, look at the reliability of the scale, and train, it will help you to reduce the random error due to measurement error. Now, let's look at systematic error. Researchers have identified over 30 different biases, and there are different approaches used to classify them. So, however, the approach is often used to group all the biases to 3 categories. It's the best. You just say, okay, they are grouped into selection bias, formation bias, and confounding. Now, just like what you can see in the flow chart, selection bias occur when there is a systematic difference between the characteristics of the people selected for study and the characteristics of those who are not. You know, that one is very simple. You know, there are many reasons people do that. Sometimes it can be convenient for convenient. Can you see that selection bias, that is under systematic error, is different from sampling error? Sampling error is not the way you sample, either systematic or not systematic, probability or not probability sampling. That one is under selection bias. Whether you use systematic probability sampling method or purpose or not probability, that is using all this purposive convenience sampling, they don't cause sampling error, because that word sampling has nothing to do with that. It just has something to do with the fact that you took sample. So the only way to reduce that is to increase your sample size. But the way you now do the sample, or sampling rather, is under selection bias. All this purposive sampling, convenience sampling, those are the sources of selection bias. So there are many of them. So some people funding, even when they say funding bias, they say, oh, we don't have money for, after you have drawn your protocol, this is how we're going to do it. They say, oh, we don't have money for that, especially if it's development work. Maybe it's either maybe pharmaceutical company or a particular organization that is funding it. It will tell you what they have funding for. So that one will now force the researcher to just, if some places are hard to reach also, if there are situations, urgency. So all those things, they affect the results. So it affects who you select, who you will not select. Those are sources of selection bias. So people study only the people that are admitted in the hospital. I think that's what they call Bergsonian bias. When you do study in the hospital on admission, you now say study done among the people with renal failure, or people with hypertension or diabetic or asthma are admitted in hospital. You find out among the social percentage responders. Don't you know that it is those people that are critically ill that come for admission? If someone is not critically ill, he has the condition, but he's not admission. So if it's difficult to generalize that of study because it can only be valid. The internal validity will be okay, but the external validity is questionable because there's selection bias. So it's those people that have critically ill, just like HIV patient. HIV patient on admission, maybe the person has developed AIDS. So it's different from HIV patient that is jumping around. Even some of them even say that they thank God they have HIV because maybe through that the process they have been employed and they are giving counseling to other people, they are enjoying themselves. So you cannot now just base your, just study only one section of them and now generalize. That will lead to selection bias. It's either it overestimate or it underestimate your parameter of interest. I actually give an example. If you say you want to study a particular group of people, like in Lagos, I usually give the example. Okay, you want to know the proportion of Igbos in Lagos. If somebody go to you select people in Ladipo, Oshodi, in a first half, you are likely to overestimate the proportion because you get a value. If let's say the value is 20%, you will get 30 or 40%. But if somebody also go to maybe area like or maybe Idiaraba, where most of them we have a lot of non-Arabs here, and go to other places where people are less concentrated, you underestimate also. You come and give a value that is there, you say it's 10%. So can you see that is selection bias? The way you select will affect the estimation you are supposed to know the parameter, the estimation of the parameter of interest. So let's look at information bias. Okay, this one just to buttress what I just said. The selection bias, the way you select subset of population, there are some things that guide you. If it's not, it's not that they came by chance, but due to some factor, you selected some due to some factors because selection bias. Now, information bias is also known as observation, classification, or measurement bias. So when you look at it critically, you may say, how is this one different from measurement error in random error? It's different. That measurement error has to do with issue of the scale you are using, how you are able to read the calibration, even sometimes the unit. You know that if somebody measure, if you measure height, somebody is measuring height in centimeter, should be more accurate than if somebody is measuring centimeter and recording centimeter. It will be more accurate than recording in meter. Even though if you want to calculate, you can change it to meter. So it will be, so the calibration, so that one is measurement error. But the measurement bias, it has to do with the way you collect information. In statistics, statistics and research, especially statistics, observation, when you say observation and measurement, actually mean the same thing. It means data collection. You say observation, make an observation, you collected data. And there are different ways, because we have different type of variables, there are different ways you can collect. All of them, you can call it observation or you take measurement. Even though you are not measuring anything as far physical measurement, it actually means the same thing. So when you say observation or classification, because when you are taking, you are collecting data also, those are the things you do. You observe, you classify, you take measurement. So any of them goes. So the way you understand them. So the word is being used for data collection. Because like when you are collecting data, you male or female, you know that you know even who has the person. Unless if you want to have, you are interested in gender, which is the social role. If you are interested in sex, you should know, well, from my drill, you know me, you know that I'm a man. You will not ask me, are you a man or a woman? And there are some situations it may be difficult. There are extreme, you look at somebody, you don't even know which one. Those cases are extreme. But when I want to know the height, if I have wings, I say, stand, let me take your height. Or I want to know your weight. Or if I need to take blood sugar from you, take the blood sample or any sample from you. Or you can have some, if there's something, okay, what did you eat this morning? That one he has to tell you. The person has to tell you that. You're going to see all those things are relevant. So when you're collecting your data, you can buy. That is why we discussed this under the logic of scientific reasoning. You use your senses. Two things use as scientists use to study your environment: your senses and your ability to reason. And it's the ability to reason that that's where you apply the statistics. But the roles overlap also, because even in trying to use your senses to collect data, you still apply statistical principle also. So you are using your sense, the 5 senses to collect data. Some you see, you don't ask, you just you record. It's a male, it's a female. Some you have to ask the person, what did you eat? What do you know about this? You need to ask the question. It depends on whatever the person tells you that you write down. Some you have to take measurement yourself. You not ask the person, but you just get permission to take the measurement from the person. You now record it. So whichever way, it's like you are observing, or you are classifying, or you are taking measurement. All of them are observation. So the process of collecting data will be a lot of error. After selection under this, you have a lot of different types. This is where you have recall bias. In recall bias, somebody that if you usually is one of the major problems with case control study. The case control study where you need to ask somebody question what has happened in the past. So well, even in the cross-sectional study also, but mainly in case control study, when you need to you need specific information about that thing. For example, now you want to know, okay, does OCP oral contraceptive cause varicose vein, varicosity? If you are selecting in case control, you have cases of varicosity. So you are asking maybe the women, did you take OCP? If the woman knows the reason you have because you have recruited the person into the study. You will not say, did you take OCP? So he will try to be thinking, can it be the cause of my problem? So you begin to read, did I take? I think I took it. He will begin to remember even what maybe they didn't even take, but they try to remember, because, or even if they take it, the person that has the problem is more likely to remember. If the control, that's the person that is the case now. In case control, you select cases, then you select control. The control, somebody that has no problem, you just say, please, we are doing a study, we just want you to answer a question. You are wasting that person's time. When you say, did you take this? I say, no, I didn't take. Even if the person has taken, I didn't take. The person that doesn't have the condition is not likely to remember that he or she was exposed to what might cause the condition. So that is recall bias. So at the end of the day, it will give impression that, all the people, it will overestimate. It will overestimate the odd ratio you calculate. They give you impression, all the people that have the varicose vein, they took OCP, almost all of them. Why it's only few, or none, the people that didn't have that, didn't take. Whereas, it's because they didn't tell you. Or these people, some of them even told you maybe what didn't exist. Even when you ask them for how long do you take, the person that have the problem can try to, I think I took it more than 2 years. They'll be telling you what might not exist, or they will likely remember to tell you. But the person that doesn't have the condition you have, even say you took it for how long, well, I won't take it like that. I don't think it's more than 1 week. That is part of called bias. It's an form of information bias. So in a situation where some people, if another information bias is where people know if you are conducting experimental research, maybe you randomize into control and experimental and control group. If you allow them to know which group they belong to, that may be information bias. This 1 minute. Sorry, ma. I'm in a Zoom meeting. I will call you back shortly also, ma. I'm in a Zoom meeting. I'll call you back. So the person, if you let the person know the group he or she belong to, if you are asking, maybe you have given a drug that will help to, to control particularly maybe hypertension, and maybe if the person has taken the drug, should be able to sleep very well, not have headache, all those things. You are asking question, did you sleep? If the person knows that it's in the the experimental group, is not being given, he's not taking placebo, he's taking the active drug. If you sleep, even if you didn't sleep, well, I slept. I slept. Because he's trying to drive to your expectation. That is a form of information bias. So the person that didn't is taking placebo, even if he slept very well, since he knows that they are not giving him or her the right drug, the active thing. Let's say, did you sleep? Yeah, I actually sleep. I didn't sleep well. So that is, it will give him, they try to give you what to expect. If you also are asking the question, if you know where they belong to, which group they belong to, you can cause information bias also. Because if somebody that is supposed, maybe this person is taking the active drug, you say, did you sleep? You say, I didn't sleep. Are you sure? That's it. Are you sure? Okay, well, I slept. Can you see? Because you have influenced the person's response. They call it response bias. So it's a form of information bias. So if it is a person that is not taking the active drug, you say, did you sleep? You say, I slept well. Are you sure you slept well? Well, maybe I didn't sleep well. Yeah, let's take it. I didn't sleep well. You see, those are the things, because you yourself, you are trying to, because you expect them, since this person is taking the active drug, you are able to, you expect particular response. Now, that's not that level. Even at the level of analysis, if the person that is analyzing it is a group experimental, and you are, why is the association? Why is it like this? Now look at the blood pressure, the hours of sleep. You are comparing. You say, no. You begin to look for a way to adjust because of your expectation. You need to look for a statistic that will bring a significant in one area, because you know what you're expecting, the group that is taking. That's a form of bias also. That is why they introduce blinding. That's the one way to remove that type of bias. When they bring blinding there. Okay, I think we talk about it. Now, there are many ways you can have the information bias, and how do you prevent it? How do you prevent selection and information bias? Same selection criteria. That is, if you are doing a study, either one group or two groups, you make sure that you have a protocol and the criteria you are here to reach. High response rate. In the situation where you are doing the study, just if your care is not taken, because especially in our own environment, people don't want to answer questions. Outside the country, in a developed country, you can even make people, those days, you make questionnaire to people. People will answer and even use their money to send to you. Even here, in our own environment, don't even sit with that person. They are not even ready to answer your question. Sometimes when the response rate is low, the people that do not respond may be systematically different from the people that responded. So that one, so if you have high response, it will help you reduce the high rate of follow-up. You know, if it's a longitudinal study you are doing, if you don't follow us also, you will not get, it will affect the response also. If you don't follow up and you reduce your data, and the people that maybe you follow up, and sometimes there are some people you don't even follow up. They come to you, if it's maybe some people are on a particular treatment or drug for you are following them up. There are some people that anytime they even come to the hospital, they'll come and visit you. Say, I just came. You have to ask questions. If you even ask them to want to examine them in a particular time, some of them will come. There's some will not come. Some will not come. So if you don't follow up, you discover that even the people that come, that you're able to get information, they may be systematically different from the other one. Maybe they are the people that have the problem much that they have to come. The other people may not have much of the problem. They feel that they are wasting their time. So follow up also. Prevention of information bias, clear definition. Yes, you need to, it's part of what to put in when you are training the researchers, the interviewers, the people that collect data. Then good measuring method. You have to use good measuring method and make sure that you train them. You well calibrated method are different. Like now, if you are measuring anthropometrics and you know that no one person cannot do the work, so you just have to train everybody and make sure that what they are measuring are not quite different. So there's a way you make sure you intra-observer and inter-observer error is reduced. Those are the ways to reduce information. Even though that one, you may be saying that one also, well, that one is more towards measurement error. The here also is they be applicable. The way you elicit response from people. That is why when you are training, you make sure you stimulate, make sure that they practice even in the training. Somebody cannot ask the question very well. How are you sure if you get to the field, you will be able to ask it very well? So blinding, that's what I wanted to talk about at that time. When I talk about the issue of response bias, so one way of doing it to blind means just to prevent a particular person from knowing which group he or she belong to or another person belong to. So if it is the single blinding is only the respondent that doesn't know which group you belong to. In that case, you have eliminated the response from that person. But you have not removed the influence of the person that is asking the question. The person can know if the investigator knows the group you belong to. He may has some, he will try to elicit some response for some people and try to elicit a certain response from another people because he's expecting them to answer in a specific way. So that is why you can do double blinding. In double blinding, both the respondent and the person that elicits the response, they don't know which group, whether this person is taking placebo or which group it belongs to, either control or experimental. They just say group A, group B, or in fact, you can use color purple and green. So purple and green, because if you say A, also people will think A should be experimental group, B should be control group. But if you say purple, green, blue, yellow, blue, green group, you won't know. So even that is, if you have single blinding, the person analyzing may still introduced bias. If you have double blinding and triple blinding rather, error at the zero stage, both from the respondent and the rest people respond, and the analyzer, the statistician, they don't know which one. They just know that there is green, there is purple. So we don't know which one comes first. We don't even know which one. So we do the analysis. Though the people that did the protocol, they will have known. They know that green is experimental, blue is controlled. They know. So, and when they deploy the treatment, they know. But at the end of the day, you can now open everybody to any people that want to know. So in doing that, triple blind. It's just to reduce systematic error, to reduce bias, so that your estimate can be closer to the parameter. Standardized procedure, quality control, all those ones, they are all related. So when you put in quality control measure, it reduces, you can be sure that even though there will still be differences, whatever everybody is taking, because most of the time when you are carrying study, it's not one person. Even the same person also, even after you have worked for a while, you are tired. What you did in the morning may be different from what you did when you are already tired, or maybe under adverse condition, if it's rainy or the sun is so much and somebody is on the field. Those are the things. So all those TJ measures to address those issues. So the number of respondents each person attend to in a day also matter. Some people, they want to cut costs, just say you must do this one. Okay. Those people, in as much that they are taking the work, they want to deliver to get their money. So if they say do 50, they will do it for you, whichever way. But how you do it, you will know. But if you if you are realistic, you'll be able to prevent all those lies. Now, the third type of systematic error, we have not discussed that and how you know, and that's the crux of the matter. Even the reason for bringing out this is because of this confounding. How we are all familiar with confounding. It occurs when a variable is associated with the exposure and the effect and affect the outcome. You see, when the variable is associated with the exposure and it affects the outcome. Now, but it is not an intermediate link chain of causation between exposure and outcome. So you can use this diagram to look at it. This is the exposure. This is the disease. So this is the exposure, this is the outcome. So that's the relationship of interest. That's what you are interested in studying. But there's another variable which is a confounder. This confounder also leads to the outcome. As this occurs when the variable is associated with the exposure, is associated with the exposure and affect the outcome. It can cause the outcome. So it's not that it's causing the. Can you see now? It's not. We have to get this one right. If you look at it, there's one arrow from exposure to disease. There's one arrow from the confounder to disease. That's also. But there are two arrows, both ways between the exposure and the confounder. That is how the relationship is. This confounder, this exposure causes the disease. This confounder also can cause the disease on its own. You can have more than one factor responsible for a particular disease. So there are two, it's just like two of those factors are involved. One is exposure, one is confounder. But the relationship between the confounder and the exposure, those two factors, is not cause effect, but they are related. Two factors can be causing the disease, but they are not related. So you cannot talk about confounder. There are two factors causing a disease, but those two factors are related. So if you are now studying one effect of one of those factors on the disease, the other one is a confounder. If it is the other one you are studying on the disease, the other one also is a confounder. That is why there are many demographic variables are confounded, like age is a confounder, because what contributes to a particular problem, aging also can contribute to that problem, like many medical problems. Age contributes, and that factor is contributing. So age, if you are studying that factor, age will be a confounder. Let's just look, we have two examples here. One example, relationship between coffee drinking, heart disease, and third variable, tobacco use. What you are interested in is coffee heart disease. Does coffee cause heart disease or contribute to heart disease? Now, you know that tobacco also contributes to heart disease. But tobacco, not that it's causing coffee drinking, but if you look at the arrow now, it's on facing both sides. They are related in the sense that you can see if somebody take tobacco, somebody take tobacco and somebody does not take tobacco. The probability that the person that is taking tobacco taking coffee is higher than the person not taking tobacco, because somehow is almost soft. The same thing, if somebody is taking coffee and somebody is not taking coffee, the probability of the person taking coffee taking tobacco is higher than the other person not taking coffee. But sometimes some people that don't want to take anything, they will not take tobacco, they will not take coffee. So it doesn't really mean that if somebody is taking, it has to take the other one. No, but the probability, that is, when we count, the probability is higher. So it's telling you, though it may not be coffee, you cannot say maybe it's the person, because he's taking coffee, that's why he's taking tobacco. No. Or because he's taking tobacco, that's why he's taking coffee. It just happened that anybody that is taking one, the probability of taking the other one is higher than the person that is not taking it. So in that case, they are related. So if you now select people, you do analytical study, like either case control or cohort study, to work case control or cohort study to know the effect of coffee on the heart disease. You know that you're going to have cases and control for case control. For cohort study, you have your cohort, you also have control also. So you can be sure that whether you are talking of cohort, the cohort you are studying, those cohort, the people that are taking coffee, the proportion of the people that will be taking tobacco among them will be higher than the people that are not taking coffee as a control. So in that case, when you now look at the association, it gives the impression the relative risk will be higher than what is supposed to be. You will think, this coffee is causing heart disease, because more, can you see the percentage of people that are taking coffee that have heart disease? Look at the relative risk. Whereas some of them also is the coffee, the tobacco is contributing, because most of them take tobacco. So tobacco in that case is confirmed. Another example here is just similar. You see, you want to look at the effect of alcohol use on lung cancer. And just like if somebody takes alcohol and somebody does not take alcohol, the probability of the person that is taking alcohol smoking is higher. You are not saying if you take alcohol, you smoke. But if you compare somebody that doesn't take alcohol and somebody that takes alcohol, probably is higher to smoking. The same thing, if somebody is smoking and someone is not smoking, the probability of the person taking smoking, taking alcohol is higher. So if you are studying the effect of alcohol now on lung cancer, smoking is a confounder. So if care is not taken, you just, can you see? Alcohol is not good, you now say, can you see? Most of them have lung cancer. You don't know, maybe most of those people that take alcohol, they are smokers. And smoke also contribute, in fact, maybe no more than alcohol, if not more than lung cancer. So that is confounder. Now, how do you control for confounder? Now, you can do a lot at your design stage, and you can also do something at your analysis stage. The one thing about the design stage is that most of the time, what you can do at the design stage also is determined by the study design. Like for example now, randomization. When you are carrying out experimental study, randomization is the process of selecting into experimental and control group just by chance occurring. Of course, that one reduce selection bias. I think I made mention of it. Randomization reduce selection bias also, because you make sure that it's by chance the person that is in experimental group and control group. Because if you don't, it's not like that. Some people, if they have relatives, maybe they feel that the new drug is good, and they have relatives that doesn't have money to treat it. They say, no worry, we enlist you. We are doing the study now. We're going to do it for 6 months. We enlist you to the group. You get your drug. That is not randomization. That is, can you see, the person just, and at the end of the day, sometimes also they purposely select people that don't have debilitated illness, that the illness is not advanced into experimental group, so that because the people that employ them to do the work, they want to get the result that that drug is better, is working. So that's not randomization. But if anybody that learn in any of the groups by chance, that's randomization. So there are different ways you can do that. So that's one way of reducing bias. Because if you don't do that, you are the selection bias coming. And that particular thing, confounding also. Because if you won't know if it's not by chance, at the end of the day, somebody, a particular people, the people that have a particular factor may also, most of them have the confounding factor also, and they give impression that it will overestimate the parameter of that. Then restriction is, okay, for this example of smoking now and whatever, and the other one, restriction, you can decide, okay, all those people that have that confounder, they are out of the game. Like for example, you want to study alcohol, effect of alcohol on heart, of lung cancer. So you may say, if you are smoking is not allowed in the study, either in the control group or the cohort group. In that case, you have removed effect from the design stage. Matching, because you may say, oh, if we can do restriction, why do you do matching? But it's not easy. Sometimes if you say restriction, by the time you get this, oh, it's not eligible because it's smoking. This one is not eligible because it's smoking. You may find it difficult to recruit. So what you can do, matching. Matching means that if you recruit one person, you find out that one person you have selected among the cohort, the smoke. Now look for, make sure the control also smoke, but it's not taking alcohol. So you are matching them so that you have equal proportion on both sides, so that the effect can cancel one another. You can now say, okay, whatever you are seeing, since they have equal proportion of the confounder on both control and the either experimental or that you can be used in both experimental and observational study, this restriction or matching. Now, the matching is done a lot with K control, a lot. But sometimes it may be difficult to match for many, especially when you are matching for many variables at the same time. It's difficult because when you get eligible person, it doesn't, you are match, you are looking for a match, you will not get. Now, let's look at method employed at the design stage, at the analysis stage. There are some situations where, number one, you cannot do randomization because you cannot perform experimental design on some situation. There are some situations, it's not ethical to do experiment. That's why most epidemiological study involving human are observational. Most observational. It's only few experiments you can perform for ethical reason. So you have to, and you still have to do the study. So most of the time you do carry out observational study. In that case, if you cannot control at the, though for some of these restriction matching can be applied to observational study, but sometimes it can be difficult. So at the analysis stage, you can control, you can remove the effect. Stratification. Stratification means just stratify analysis. So, like for example, now when you have two groups, one group, they say is, you know that you are looking at effect of alcohol on lung cancer. So, you know, some take alcohol, some to take. So you can first of all run the analysis for two take alcohol separately, run analysis for those who do not take alcohol, stratify, and that's why you have common horde ratio. And in the training we'll be doing on logistic regression and merging with stratify analysis. It's on stratify analysis and logistic regression. How do you do that? And now that's when Mantel-Hansen chi-square comes in. Because that's the only one we have not treated in our chi-square because it's related to stratify analysis. and it is where we do our workshop on logistic regression. We merge it with stratified analysis. We do that. Statistical modeling, that is using regression. That is, and that's why many people want to, and that's the reason what you use to remove confounder, multiple regression, either multiple linear, multiple modeling, generally, to remove the threat of confounder. It may be multivariate analysis, but many people, that's where many people, the terminology issue. Multiple regression is actually multivariable analysis. The multivariate analysis are multivariate analysis of variance like MANOVA, and multidimensional scaling, factor analysis. Those are multivariate analysis. Simple multiple regression, either linear or logistic, are multivariable analysis because you have only one outcome, but you have many exposure. But in multivariate analysis, you have many outcomes, many exposure. So multiple linear logistic regression, they are actually multivariable analysis. But you can only get what I'm saying is standard. If you read standard textbook on statistics, I will tell you that. I think we should stop here so that we can entertain questions. How you now do that? The statistical modeling, the regression, it is when we get to the regression. So that is the lecture I actually give. Even in that regression, so I actually give you so that people, why do you want to do multiple regression? Why do you want to do it? You know the reason behind removing the effect of confounder. Because it is when you only remove the effect of confounder, when you now run the regression for both factors, if you run for each of them separately, both the factor and the factor that's confounding also, if you run them separately, they will give you value. In fact, it can be overestimation or underestimation. But when you now run them together, you remove the effect of comparison. You'll be able to see the effect of each person, or each factor on the outcome. It's through multiple regression. You do that. I think we can entertain question now. Yes, 3 people chatted. T, okay, join. T stand for what? Sir. T, where did you see T? You see T stand for what? Is there any T in this thing? Then, good evening. Please, can you kindly explain the formula I use? Wait, sir, please explain. Okay. Then first, this thing. Okay, it's because they are late. I was wondering. Okay, I'll go and explain. Explain randomization again. It is not clear. Say, okay, good evening. In the past, you try to distinguish general and generalized linear model. What is the difference? Yes, but that one I did it in, okay, it's Prof that's asking, okay? Thank you. Okay, let me start with what I may not need to open the slide. I will go back for those first 2 questions. I will go back to the slide, explain the T. Randomization. Randomization, when you want to, you are doing experimental study. By nature, experimental study is not without comparison. It's not without comparison, but sometimes you now overcome that issue by using the same people to do repeated crossovers. Can do, even when they do crossover study, they still random, better to do dependent when they have one group receiving the 2 treatments at the same at different time. So in that case, you are not talking of any randomization because you are not divided, you only have one group experimental study. But you still have your measurement 2 times. So there's no experimental design without comparison. So when the group you are comparing also are independent, 2 separate or 3 separate or 4 separate groups, they are not the same. You need randomization is selection into those groups just by chance. You make sure either you do balloting, whatever way you do that, the person that go into group A is not because you know anything, but it happened to be just by chance. You're like they put paper, they now say everybody just pick. You put red, blue, green. No, people just pick. When you pick, so it's by chance. But it's not because of selection bias. Selection is purposeful. No selection. Somebody put this one here because of it. So selecting into experimental and control group just by chance is randomization. That is the meaning of randomization. Now, okay, the word Prof asked. Now, generalized linear model. I don't want to open that slide here. It's very simple. General linear model. General linear model is just a form of more like equation used to explain the relationship between a continuous outcome. A continuous, that is, the outcome is a continuous variable. And the factors responsible. If you look at it under it, you see linear regression. ANOVA is there because, you know, we talk about factorial ANOVA. You can have many factors and the outcome is still continuous. So when you see linear regression, ANOVA is general, they follow general linear, and some other multivariate analysis of variance when the outcome is continuous, follow general linear model. But you know, most of the development in statistics, most of them usually start with continuous variable, quantitative variable. Before intelligent people also now, okay, how do we adjust this to suit categorical variable like correlation? The first person to describe is Pearson. He described Pearson correlation, product moment correlation coefficient. And Spearman and Kendall, they now came also to apply it to when the variable is not continuous, it's not parametric. They now adjust. It's the same thing, linear regression. So we now adjusted to bring in logistic regression. So general linear model look at outcome, continuous outcome, how you can predict continuous outcome. And ANOVA is there, MANOVA is there, this ANCOVA, all of them, they are under that and linear regression. But when people now try to adapt it to suit even categorical variables, something that don't even follow normal distribution and are not continuous. So using a survivor, using Gaussian regression, Gaussian regression, the outcome is rate. When you are calculating rate, the outcome is rate. And Gaussian regression, logistic, the outcome is categorical. So you now adjust the same formula to accommodate all those other ones, but there must be a function link because there I don't follow normal distribution naturally. There's a function link, so it now becomes generalized linear model. So whenever they put this function link to accommodate the other things that are not outcome that are not continuous, so that is generalized linear model. So when you talk about generalized linear model, it contains all of them, both continuous outcome and not continuous outcome. It contains all of them. Logistic regression is there, Gaussian regression is there. So they are under generalized linear model. But the general linear model is the one that is the origin. It's the generalized. So the general talk about continuous outcome. I think I've answered that one. And then thank you for this. Okay. Huh? Age adjustment done. Age adjustment. I don't know what you mean by age adjustment. But if you want to control for age, you mean control for confounder. So when we talk about it's very simple. If you want to, we have already said you can match. If you match, you make sure that if somebody that is in your group, experimental or any group, or your experimental group is 35, you now look for somebody you may say, okay, you don't want the difference to be more than 5 or 3 years. It can be led maybe from 29 to 30, you say 35, but maybe from 33 to 37, you just give that range. So you now look for a match. So by matching, you control for confounder, age as a confounder. Matching is what you part of the method you use during the design stage. If you don't do that, you don't analysis. You involve also age in the multiple regression to remove the effect of age. Okay, I think let's go into. Let me show that first the slide. People are asking. Yes. Okay, this is the one people are asking. There's no big deal there. It's even the simplest of it because you came late. We just say we are talking of error. Error is a difference between a measured quantity and a true value. If something is 5 and somebody says 6, the error is 5. It's 1. That's 1. If somebody says it's 4, the error is -1. So if the prevalence of anemia is among children under 5 is 30%, and somebody says 35, there's an error. But it's only God that knows the true one. If somebody now say 16 is 30, somebody says 29, there's an error, even though it's very small. If somebody says 20, there's an error. So when there's a deviation between what the true value and the value you now bring out, you calculated, it's error. The difference is the error. So error is not mistake. It's a mistake. Error is different from mistake. The error can come as a result of mistake, but the error is different from mistake. Mistake has to do with somebody's action. So you see that sometimes even in inaction, every action, inaction, there can be error without even you contributing to it. So we now say that there are 2 types of the error: random error and systematic error. The random error, the E is the error. Random error, ER. Systematic error, ES. Random error is due to chance. It's due to chance. It just occur randomly. That's the real name. Randomly. It can just happen by chance. It just happen what you didn't expect. It can just happen. Of course, you can reduce it also. If you know that something can occur by chance, you can prepare for it. When you prepare for it, doesn't mean that you will be able to eliminate it completely. You can only reduce it. You can reduce it. Why systematic error is systematic in the sense that it's the way you carry out your study. You can actually remove it according to people, but to me, you cannot actually eliminate it, but you can reduce it much more than random error. You can reduce systematic error if you carry out your study very well. So I usually tell people who knows everything, even the best of best is still learning. So if you are doing a study, you can become better and better and better. So if you are becoming better and better and better, you over 10 years, okay, what you did last 5 years, and you prove that you have removed systematic error. And when you do another study, you remove systematic error more. That shows that you didn't remove all the systematic error then. So to me, you can reduce systematic error more than reducing random error. So that's where and the systematic error, SES, random error, ER. I think that's the formula people are asking for. I don't know if there's any other question or any other. You can ask question physically. You can ask question. But if you don't want to ask, you can type. You can just type. If you don't want people to see it, you can. No question is stupid, right? You are here to learn. So you can ask your question. Do it privately to be just chat it to me. I will not read the name of the person that asked the question. I will just read the question and answer. Yes. Okay. There's no other question. If you want to ask question, you have to unmute yourself. Otherwise, we will not hear you. Unmute yourself. I ask your question. Any question? Yes. Go on. So, Jane, are you asking a question? Because your name just talk.
Yes. Good evening, sir.
Okay, go on.
Okay, sorry, I'm joining late. So maybe I may have missed some vital information that have been
passed. Now, if you are late,
I just wanted to find out the training you listed on the WhatsApp platform.
Yeah.
when are they coming up this week? The one for this week, what date is it starting?
It's there. If you read, it's Friday to Sunday. Friday 6:30 to 6 to 8:30 rather. 6 to 8:30. No, Friday to Sunday 6 to 8:30. Friday to Sunday. That's when Charlie do our training. Friday to Sunday 6 to 8:30. So that one using SPSS and see any other, because I don't want the length of the something. If no other technical question, so that I can just stop recording. I don't want to lengthen the I'll make the length of the video to